Hey, how are you? Yes, I'm the speaker at 10. All right, great. Thank you. Is it on? Is it working? It used to be work about half an hour ago. Maybe it's just falling asleep after some inactivity.
Just check.
So was it the batteries?
Yeah, they're working now. You need some?
I don't know anything. Well, if you have this pointer, but he said you don't. That's all right, man. Or a very long stick. Sorry. Nah, just kidding. And I can poke somebody that's asleep. Like one of these old-fashioned radio antennas, you know, that you would pull them out. Oh, I see. So that's the distribution. The people that want to pay attention come in the front, and the people that don't want to be bothered go into the
Theorem side.
All right.
Where are you from, sir?
I'm originally from Romania. I work at WITS now.
Okay, look at this. How you find South Africa?
It's interesting. I like it.
When last have you been back to Romania?
Oh, I left Romania a very long time ago, in 1992. So since then I lived in France, the US, Germany. I lived in Mexico for 14 years.
Mexico.
Yeah.
You speak Spanish?
I speak Spanish, yes. I speak French. My German is a bit rusty, but I get by.
So what do you do at WITS?
I'm a research professor. I don't even teach. Isn't it ironical that I'm at this conference?
But is this your topic for today?
That's my topic for today. Yes, I'm the SAM speaker, so I'm supposed to give a talk a bit more mathematical, I think. So
Sure, they'll find it interesting.
let's hope so. I gave a workshop, and some of them said it was too hard.
It's really difficult.
Yes, I know.
So
So I have 5 more minutes. Is there anybody going to introduce me, or at 10 I just start speaking? What's the procedure?
wait until 10. Normally Dr. Mahar.
Okay.
Coordinator comes in.
All right.
I should actually go check for you.
All right. That's fine. I'm here. I'm not going anywhere.
Slightly make it softer because I can always boost it on my side, but once if it's any distortion, then I can't do really anything.
So were you
about
picking
that.
up something?
Yes. Okay. I think that should
I think
be
it's
fine.
better now.
Yeah.
You want to put it
Oh,
more
sorry,
in the
the
down
bottom.
one? Yeah, I have several.
There we go. Looks like you're going fishing with this jacket.
Exactly, I am.
Okay.
I'm going fishing now. I'm going to fish some people from the audience. Hello.
Mr. Nathan, I come from Conjecture. I've got someone who was attending this conference here. She was standing here, but she lost her cell phone. Now CCTV, she sent me there.
So what do you need? You need to find the cell phone.
I want you now to stand. Then CCTV, she showed me exactly. We met with to rewind the camera, move the camera.
Well, I talked to these guys. You see, they are, I'm the speaker. They are the people with cameras and so on.
All right.
So let's spoke to them. Hey guys, this man needs some assistance.
Sorry, sir. The sound.
And since then,
Hey, how's it?
all right. Since then,
All right. That's fine. Okay. Are you going to introduce me? Yes. Okay. He's going to do it.
Good morning. Good morning, colleagues.
Thank you.
Welcome to this last and final plenary for Congress 2017. Our plenary speaker this morning is Florian Lucas, who is a research professor at the University of Witwatersrand, who has authored more than 500 papers in mathematics and co-authored 200. If I recall at the SAMS conference, which I attended last year, I think he was one of the people on the top echelon in terms of the leadership in mathematics publications. He is a Romanian mathematician who specialized in number theory with emphasis on Diophantine equations, linear recurrences, and the distribution of values of arithmetic functions. He has made a notable contribution to the proof that irrational automatic numbers are transcendental and the proof of a conjecture of Erdos on the intersection of the Euler function and the sum of the divisors function. Colleagues, it is very rare to get an expert of this nature to grace and present at an AMESA conference. He is, by the way, a speaker on behalf of SAM, the South African Mathematical Society. We have a partnership and an arrangement and work together. So when they have the SAM conference, we also send a previous speaker from the Association of Mathematical Education of South Africa to them. So this is a joint venture. I would like to present to you Florian Luca, and his topic is squares with intersecting digit patterns. Interesting digit patterns. Yeah?
All right, thank you guys. Thank you very much for the kind introduction, and thank all of you who are sticking around and coming to my talk after last night's party. So, as it was said, I am a research professor. I don't even teach. I seldom teach, which is a bit ironic that I am a plenary speaker at the Mathematics Education Conference. However, I do meet some of you at towards maybe the more advanced part of your curriculum. Because of my preoccupations in mathematics, I'm interested in properties of numbers. You see, numbers, we can look at some family of numbers, and we can ask questions about this family of numbers. You take your favorite numbers, and you can ask, are my favorite numbers perfect squares? Or are there any primes among my favorite numbers? And every now and then, the question you're looking at is silly. For example, if your favorite numbers are even, then you're not going to find too many primes there, correct? You're just going to find the number 2, and that's it. There's no other even prime. But sometimes the numbers are a bit more interesting. And because of that, you can not only address everybody with some knowledge in mathematics, but you can get people and students to make conjectures and to try to guess the answer. And some of the things can be proved at an elementary level in high school. Some of the things make very tough research papers. Some of the things are unknown. So last year at the SAMS meeting, I was speaking about numbers for which their divisors have interesting properties. I was speaking about perfect numbers. Do you guys know what perfect numbers are? Raise your hand. Who knows what that is? What's a perfect number? It's a number that's equal to the sum of its divisors. For example, 6 is a perfect number. Its divisors are 1, 2, and 3, and they sum up to 6. So I was giving a talk about that. For today, I prepared something about digits. I gave a little workshop with digits a couple of days ago on Tuesday. So what I'll be looking at, I'll try to create squares that have digits which I think they are interesting, at least for me, and I hope you will also find them interesting. So here's a problem. Start writing down all your squares, which are 1, 4, 9, 16, 25. What's the next square? 36. What's the next one? 49, exactly. Then I'm going to challenge you to single out the ones that have only odd digits. Only odd digits. It has no even digit in it. 1 and 9, they work. Can you find others? No. Well, let's solve that problem together. So we eliminate, since I want numbers which have odd digits, in particular the last digit is odd, so that would make the number odd itself, right? If a number is odd and square, then it has to be the square of an odd number, correct? So let's just start squaring out odd numbers. I'm going to square out 1, I get 1. I'm going to square out 3, I get 9. And then I get the numbers that are written there. 25, 49, 81, 121, 169, 225. What do you notice there? Can you make a conjecture? of what I've shown you. So the last digit is always odd, but what happened to the digit before that? It's even. Do you think that's true? That is always true. Let's prove it. So let me take the number that I'm going to square it, which I'm going to denote by x. I'm sorry for the language, but I am a SAM speaker, so I'm supposed to write some symbols there. So there's going to be a little bit of algebra in this talk. So let's write x. Let's say the last digit of x is the letter A. A is some number between 1, 3, 5, 7, and 9, because that's a digit. And then 10b is the part of the tens, is the multiple of the tens. And let's square that. I square that out. I use the formula of the squares that I know. The square of 10b plus twice times the product of the two guys between the square and the square of a. Now the square of a, we calculated it before. We know what it is. It's one of the numbers 1, 9, 25, 49, 81. It's one of the numbers for which the penultimate digit is even. Now, if you look at 100b squared, that's not going to contribute to the last digit, correct? Or to the previous last digit, because it's a multiple of 100. If you write it down, it's going to end in 2 zeros. So when you put it to the sum, it's going to do nothing. What happens with the number 20ab? Its last digit is 0, but the previous digit before that is what? It has to be even, because it's a multiple of 20. So it's a number that ends up in something like 20 or 40 or 60 or 80. And then it's that a squared, which has 1, 9, 25, 49, 81. Now imagine that you put these three numbers together and you do the sum. In the very last digit, the unit digit, you're going to get an odd number because it's the unit digit of a squared. But the digit before that is going to be even, because you're going to add the 0 from 100b squared with something even from 20ab. And with something even from those guys, 1, 9, 25, 49, 81. So that is the answer. The answer is that the only squares whose digits are all odd are just 1 and 9. And in some sense, I lied to you, because you see, the theorem is that if you take the square of an odd number, then the penultimate digit is always even. That's also true in 1 and 9, except that you don't see it, because you don't write it as 0, 1 or 0, 9. If you would, then you would say, aha, the theorem works for that number as well. But that number is too short. That's why I didn't write it, but it is there. All right, so in some sense, the previous solution shows that all perfect squares have either the second digit from the right even, that's if you take the square of an even number, the second digit from the right even, exactly, except in the case of 1 and 9. So the problem is not new. There is all these things, you collect them. There is things on the internet. There is a thread called Ask Dr. Math on the internet. Then for these problems with digits, there is all sorts of websites that collect problems from maybe competitions. For example, MathLinks is one like that. Or the art of problem solving is one like that. You could just Google that and go in, and once you go in, there is so much stuff there. There's forums where people ask questions. You find some interesting pattern. It sounds elementary. It sounds like it's something that's known. You can just go in there and post your question, and somebody might answer it. In 1954, a Hungarian mathematician called Richard Oblath, he proved that the only perfect powers, not only the squares, but only cubes, fifth power, sixth power, and so on, whose digits are equal to a fixed one, which is not the number 1. The number 1 was difficult for him, were only 4, 8, and 9. So what does it mean all digits are equal to a fixed 1? Such numbers are called rep digits. For example, 11 is a rep digit. 222 is a rep digit. 5,555 is a rep digit. So you take some digit and you repeat it as many times as you want, and you get some numbers in this way. And you ask which ones of those numbers are squares or cubes and so on. And if that digit that you're repeating is not 1, this guy, Richard Oblath, he proved that the answers are only numbers with 1 digit only, and which are also squares or cubes, which are 4, 8, and 9. For example, now with our limited knowledge, we can already show that if I have a square, all whose digits are repeated, then that can be only 1, 4, and 9. Let's solve that problem. So let's take a square, and let's suppose that I have all the same digit, which is repeated m times. Now, if that repeating digit is odd, then I get the previous problem, correct? So I said, aha, the previous problem, I already solved it. I know that the only squares with odd digits are 1 and 9. So that's the end of the story. So from now on, I can suppose that the repeated digit is even. Of course, I have the number 4 in there, which is too short. It just have one digit, and that's a square, so that's fine. Let's suppose that we find bigger examples. So let me list out what the bigger examples would be. So I have at least 2 digits, and I take this digit and I repeat it m times, where the digit is 2, 4, 6, or 8. And these are the strings of numbers that I get. Now my challenge to you, can those ones be squares? For example, can you have a square that ends in 22? No, because 22, numbers that end in 22 are not a multiple of 4. They are even, but they are not a multiple of 4. So if you have an even square, that certainly has to be a multiple of 4. The same thing happens to 66. Numbers that end in 66 are not multiples of 4, so they can't be squared. How about 88? Well, those ones are multiples of 4. So there we seem to be a little bit in trouble. However, they are not multiples of 16. Write a number which is a bunch of 8s, factor out the 8, and then you just have a string of 1s, which you can write down what that is. It's decimal. So a string of 1s is just the decimal representation. But if you want an algebraic formula for it, it's going to be that sums of powers of 10. And if you look at that sum of powers of 10, you have a bunch of powers of 10 which are all even, but you slap a 1 at the end of it. So that's going to be an odd number. So that number that I've written there, it's 8 times an odd number. Can that be a square? Well, 8 is the cube of 2. So I think about unique factorization. I take a number, I factor it in prime factored. When is that going to be a square? Only if the exponents that I put on the primes are all even. Since 8 is 2 to the cube, and 3 is an odd number, that cannot be a square. So I've gotten rid of the 8s also, so I'm left with the 4s. So I have a bunch of 4s sewed up together, and that's a perfect square. It's the square of x, correct? But that number is even. Therefore, since x squared is even, x is also an even number. I write x like 2y. I square that relation, I get x squared equal 4y squared. And now I can cancel the 4s. I can cancel the 4 from the 4y squared, and I can cancel the 4s which are on that formula 1 there. And I get a square which is a bunch of 1s. What is that? That's the problem I started with. I said that doesn't have any solutions if I have at least 2 1s, because that's a number that has at least 2 digits, and all of them are odd, and it's a perfect square. So I already proved it for you. You see, it wasn't that hard. The case a equal 1 in Oblast's problem, but I only did the squares. If you want to do the perfect powers, what you're looking at a bunch of 1s, which you have some formula for it there, 10 to the m minus 1 plus 10 to the m minus 2, and so on. You can collect all of them together and write it as 10 to the power m minus 1, everything over 9. And you ask that expression to be a perfect power. But you see, perfect powers are more difficult. They are not just perfect squares. That's some number, which is the base of that perfect power, to some exponent, which is greater or equal to 2. Well, believe it or not, this problem had to stay there for about 50 years. As I said, Richard Oblast did everything except the digit 1 in 1954. These 2 French mathematicians, Yann Bougeot and Maurice Mignot, showed in 1999 that what we call a Diophantine equation, it's an equation in a bunch of unknowns, which normally you won't be able to solve. You usually solve one equation in one unknown. If it's linear, it's very easy. If it's quadratic, it's a bit harder. If it's a polynomial of a higher degree, you have to compute roots, so that's also harder. But if you have a bunch of variables like x to the power y equal 10 to the m minus 1 over 9, that is much more difficult to prove that there is no 3 such integers. And they proved that. All right, so what I did, I said, OK, fine. I can't just find one digit and repeat it a bunch of times and get squares, but maybe I can do something. How about if I start with 2 digits and repeat them a bunch of times? Let's see, what are the numbers with 2 digits? Let's list them. 10, 11, 12, and so on. So I take those numbers and I concatenate them. So I get the number 1010, which would be 1010, or 1111. This one we already talked about him. Or 1212, or 1313. And I keep on listing them. I have 90 numbers like that. The last one is 9999. Is any one of them a square? Well, you can take out your little calculators, and if you're very fast, you can take the square roots of those 90 numbers, and you can see if you find an example. Or if you have some computer program, you can make the program compute it and run and select the cases in which this is true. But I don't want to do any of that because I'm a lazy guy. I do not want to do any computations. I want to guess them rather than compute them. So let's say that that number is number A. This is why we invent algebra for, right? Algebra was invented to give some symbol to some number that lives in a collection. So we do not have to go through the entire collection. We can just push the symbol around and see if we get some answer. So what does it mean to take a number with 2 digits, which I call it A, and to concatenate it with itself and get a number of 4 digits? What that means is that I take the A, I multiply it by 100, so I shift it. Now I have 2 zeros at the end, and I put 8 back there in the tenths and the units place. So that number is the 100A plus A, which is the same as 101A. And I want 101A to be a square. So 101A is a square, fine. So now I look at the number 101. And 101 is a prime number. So that prime number 101, which sits on the left, divides the square of x, which sits on the right. And now I use a theorem that comes from, if you want, a fundamental theorem of arithmetic, that every number can be factored in a unique way. If I have a prime that divides a square, then that prime is going to divide the number before having squared it. So every square which is a multiple of 3, it's in fact the square of a number which is a multiple of 3. So in particular, since 101 is prime and it divides the square of x, it has to divide x itself. So I can write x as 101 times someone else. Let's call it y. I insert that into my equation too. I get 101a is 101y everything square, which is the square of 101 times the square of y, and I can simplify 101, but there is still another one left. So a is 101 times someone else, and that someone else is an integer, is at least 1. So this makes a at least as big as 101. However, a was at most 99 because it's a number of 2 digits. So I already got the contradiction, and I didn't have to take square roots of those 90 numbers. Also, this gave me a little bit more leeway, because now I can go and I can do the same for 3. Because you see, for 3, the situation is more complicated. So I start with 1,000. So the number I created is 1001,001. And the next one would be 1001, 1001. And all this, and I'm asking if these things are squares. These ones already have 6 digits. So let's do it in the same way as I did with the previous one. I write it as, since it's a number with 3 digits and I'm concatenating it with itself, I take 10 power cubed and I multiply it by a. So I take a, I shift it to this side, I put 3 zeros at the end, and then I put another copy of a back. Now this number is 1001 times a, and that's equal to the square of x. Well, 1001 is not prime. 101 was, but 1001 isn't. It's divisible by 11. So you can factor it. It's 11 times 91, which is 7 times 11 times 13. Such a number is called square-free. What is a square-free number? A square-free number is a number so that if I factor it, every prime appears exactly once in its factorization. Let's see how many of you are following me. Is 12 square-free? No, why not? Because it's divisible by 4. Very good. You guys are following. Amazing. So yes, 12 is 2 squared times 3. Because of that square on top of the 2, 12 is not square free. 1001 is square free. So suppose that 1001 times a is equal to the square of x. And let's do the argument that I did before with 101. I look at the number 7 that sits on the left of that equation as a factor of 1001. And I say 7 divides the square of x. Therefore, x itself is a multiple of 7. But what was special about 7? Nothing. It's the same argument for 11 and the same argument for 13. Those ones are primes that appear exactly once when I write down 1001 as a product of primes. So that means that all three of them, 7, 11, 13, each one of them divides x. Therefore, their least common multiple, which is their product, divides x. So I get that x is a multiple of 1001, exactly the same as before. So then I get 1001a equal x, which is 1001y, everything square. I square that. I cancel a factor of 1001. I still get that a is a multiple of 1001. So it's bigger than 1000. It has at least 4 digits. But it should have had at most 3 digits. So again, it's false. So you'd say, oh, well, buddy, I don't think you're going to make it. The way you're going, I don't think you're going to find anything. That's because the calculations are going to be more and more difficult. And then at some point, you will have to give it up. Well, you see, the calculations do become more and more difficult. But that sort of suggested to me when I looked at that 101 was prime. That was some accident. 1001 was not prime, but for him it didn't work either. But for him it didn't work because it was not a prime, but it was square free. So then what I say, let me try a length so that if I take 1, 0, 0, 0, 1, so instead of having two digits or 3 digits, let's take that number of digits. So that if I have that corresponding power of 10, so 1, 0, 0, 0, whatever 1, then that number is not square free. It's something like 12. Maybe it has a prime factor that appears there square. Because if I could do that, then maybe I have a better chance of actually creating something. So here's what I do. I make my life easier because I don't know how to factor x squared plus 1. I don't know how to factor 10 squared plus 1 or 10 to the 4 plus 1. So let me take an odd number, just 10 to the m plus 1. M is odd, like in the case 3. And then I have some formula there. If m is an odd number, then I can factor x to the m plus 1. And the factor x plus 1 comes into the front. So if you know that formula, that is good. If you don't know it, you can just accept it and you can check it. You can check that if you expand the right-hand side, you get the same as the left-hand side. Because if you expand the right-hand side, you get all those signs powers of 10 multiplied by 10, and then you multiply them by 1, and because of the signs, all sort of middle terms cancel. It's something called telescopic, and you just get left with the biggest power of 10 and with the smallest 1. So the first factor in the right is 11. So then I say, well, let me make that enormous parenthesis to be a factor of 11, to be a multiple of 11. How can I do that? Well, I group them in some way. I group the first 2, so I have a 9 there. I group the next 2, and I have another 9, and so on. So I can write down the decimal expansion of that number. It's 9090, and so on, up to the end, except that at the end I add a 1, so it's 91. Now, do you know the criteria of divisibility by 11? Who knows the criteria of divisibility by 11? You should have come to my workshop. I did it there. There's a criterion of divisibility by 11, which is similar to the criterion of divisibility by 9. Who knows the criterion of divisibility by 9? If I give you a long number, can you tell right away if it's a multiple of 9 or not? Yes, how do you do it? You sum up the digits. You get a smaller number. And if that one is a multiple of 9, then you win. Well, guess what? There is one similar for 11. I'm not going to prove it. I'm leaving it to you as a homework. If I have a long number, no matter how long it is, you take the signed sum of the digits. So you take the first one, you subtract the second one, you add the third one, you subtract the fourth one. It looks almost like the divisibility by 9, except that those signs. Well, if the number that you get in that way is a multiple of 11, then your original number is a multiple of 11. Think about it. For example, 55. Any number with 2 digits, it works because it's 5 minus 5, and you get the number 0. If you look at, let's say, 121, which is the square of 11, is 1 minus 2 plus 1. It's again the number 0. It doesn't always have to be the number 0. For example, 803 is a multiple of 11. It's 8 minus 0 plus 3, which is 11. So this criteria allows one to look at some number in the same way as you do it for 9s, you can do it for 11s. So let's look at the number that I wrote there, which was a bunch of 9s, followed by 0s, and the 1 at the end. So you see, if you alternate it, you take that 9 and you subtract a 0, because that's the next digit. Then you take again the 9 and you subtract the 0, and so on. And you have to keep track of how long it is. So the total number, the length of the total number was the number m in here, because it started like this. It had m terms up there, and m was an odd number. So you have to keep track a little bit of what you're doing. There's m minus 1 over 2 of those 9s, and then you subtract another 1 at the end. So there's some formula for that number, 9m minus 11 over 2. And I want that to be a multiple of 11. So 11 is already there, therefore I have to find the multiple of 11 inside 9m. And that happens if, let's say, m equal to 11. So let me take m equal to 11. So I know that for m equal to 11, 10 to the 11 plus 1 is divided by the square of 11. Why is that? Because the 11 I get it for free, correct? The 11, I just get it from this formula. I have that 11 in there. But the square of 11 comes because also the long parenthesis is divisible by 11. So you see, now it's a better problem, because since that 11 square is there, then I no longer have to worry about him. I know, of course, 11 is going to divide x. But in some sense, now I don't look at 10 to the m plus 1, and that was square free. I'm looking at a shorter number, which is 10 to the 11 plus 1 over 11 square. And even if that would be square free, I probably still can win. And I write down what it is. It's 826,446,281. I factor it in my head, just kidding. And I get a square free number. So fine, then I repeat the same argument as before. I have 11 squared times a times that number n, which has 9 digits. It's a square of somebody. N is square free. Therefore, n has to divide x squared. Therefore, n divides x. So my x is 11 times n times y. And I write down that formula, and I get that a is capital N times y squared. And you think I'm not going to win. But hey, I'm telling you, I'm going to win. You know what? Because a can have 11 digits, and n only has 9. So I can still stick something to it to make it 11 digits. If I take y to be equal 1, 2, or 3, I get a number that's too short. But if I get y to be equal between 4 and 10, ta-da, I'm winning. Look at those numbers. So the first one is the number 13223140496. If I stick it itself there, so another 13223140496, then I get a perfect square. I get the square of 36363636. Look how beautiful that looks like. So it did seem like I wasn't going to get anywhere, but I was perseverant, and I didn't stop at 2, 3, or 4, because sometimes you have to go quite far in order to find something. But I haven't really used much. I mean, I use things that you could explain to learners which are interested in following, for example, in questions in arithmetic and so on. It's probably difficult to challenge somebody to come up with such an argument, but seeing it and understanding it once it is presented to you, then, so I leave it as a homework. I leave it as a homework to you guys that you can find infinitely many examples in this way. It's not that hard. All you have to do, you have to find infinitely many primes and exponents m, so pairs, a prime number p and an exponent m, such that the square of p divides 10 to the m plus 1. I found p equal to 11 and m equal 11, and 11 squared divided 10 to the 11 plus 1. Once you can do that, then what's going to happen is that once you get by this stage over here, whoops, I'm going the wrong direction. Once you get to this stage over here, your number is going to look like 10 to the m plus 1 over p squared. And that number is going to have less than m digits. So you can multiply it with some appropriate square, y squared, in such a way that after you have multiplied 10 to the m plus 1 over p squared with some appropriate square, which is not too small, not too big, it ends up being a square, that has exactly the correct number of digits. All right, so let me move to a different problem. So you see, since I like these problems like this, I pick up things where people propose problems. There's many magazines in the world where you can find problems. In the American Math Monthly, Crookes Mathematicorum, College Math Journal. They all have problem sections. This one, I found it from a journal called Mathematics and Computer Education. It was a little remark there, which was in the spirit of what I have been doing so far, which said, look at the number 183. If I take 183 and its successor, so I don't concatenate 183 with itself, but I concatenate it with the next number in the list, I get 183, 184, which is a perfect square. The problem did not ask to characterize when this happens and so on. It only said, can you find other examples? It turns out this was the smallest example. You can't find examples with 1 or 2 digits. So let's see why. And I like that problem, so I wrote a paper. It ended up being a 15, 20-page paper, which I sent it to them, and they published it. So let me tell you what's in that paper. So basically, that paper kind of inspired me. It also did it for not concatenating, not adjoining one, or you will see what else will follow. So let's try to do it with numbers with 1 digit. So why do we have to go so far with 3 digits? Let's try a number with 1 digit. Take all the numbers with 1 digit and stick at the end of them the next number. So you take 1, you get 12. You take 2, you get 23. Take 3, you get 34. 45, 56, 67, 78, 89. That's it. I don't have other one. Do I find squares there? No, there's no square in there. Let's take numbers with 2 digits and concatenate the next number. So 10, 11, 11, 12, 12, 13, and so on. I go all the way to 9,899. Do you think I'm going to find a square in there? Well, you can make a guess, yes or no? No, there's no square in there. So you see, once you go there, then you say, oh, well, let me try to understand why 183 works rather than just trying to blindly look for them. So let's go again from the, let's say, brute force approach. Let's do some representation of the problem in which I take the number a, it has m digits, and I stick in the number a plus 1 at the end of it. So let's try with 3. Let's take an a which has 3 digits. So what does it mean a plus 1? I take a, I multiply it by 1,000, so I shift it to the left, I put 3 zeros at the end, and then I stick a copy of a plus 1 there. I want to make sure that I don't start with 999, because then if I add 1 to it, it becomes too big, right? So this one, you see, one of my contributions to mathematics is that if I see a 1 in one side of an equation and a square in the other side of the equation, then I move the 1 in the side with the square, and it factors. And that observation is very important, because if you can factor an expression, then you conquer the expression, and probably you win. So I group a times 1,000 with a itself. I get a times 1,001, and I put the 1 in the other side. I get x minus 1 times x plus 1. So then I say, aha, so I need a number with 3 digits. So that when I multiply it with 1,001, there is some factorization of them. I can split it up in prime factors. And I can group those factors in some way such that one of the number becomes x minus 1 and one of the number becomes x plus 1. Who x is not so important at this stage. What's important is that I can group them as a product of 2 numbers that differ by 2. And I already factored 10^3 plus 1, which is 7 times 11 times 13. And let me go to Sastri's example and say, let's a equal 183. Let's understand why it works rather than how he found it. So then maybe he found it by brute force, but let's not try to find it by brute force. So factor 183 as best as you can. It's certainly a multiple of 3. Divide by 3, you get 61, and you can't divide further. So let's collect all those numbers there. You have 3, 61, that's a. You have 7, 11, 13. You have a product of 7 guys. Group those 7 guys in some way such that some subset of them multiplies to some number, the remaining subset multiplies to a different number, and the difference between those 2 answers is 2. Well, guess what? 61 times 7 is 427. 3 times 11 times 13 is 429. The difference between them is the number 2. The number that sits in the middle is 428. That's why it works. That's why 183 times 184 was 428 squared. So now that I understand why it works, I can ask, how can I create other numbers in that way? So sometimes an example is very important if you look at it the correct way. So then, what was important there? First of all, it was important that I grouped x squared minus 1. I wrote it as x minus 1 times x plus 1. Then what else was important? I knew the factorization of 10 cubed plus 1. It had some numbers in it. It had 3, 7, and it had, right? It had 7, 11, and 13. And I also knew the factorization of the number a. It had 3 and 61 in there. So I said, instead of trying to find a coming out of some equation, try to break a into two pieces in the same way as 183 came as 3 times 61. Maybe the answers to this problem do not come from some linear equation, but rather come from a writing of a. You take your number a, which you don't know what it is yet, and you try to write it as a1 times a2. You don't know what they are either, but you know the number m, 10 to the m plus 1. You should break it up into two pieces, u1 times u2, and a is broken up into two pieces, a1 times a2, so that if I group some piece of 10 to the m plus 1 with a piece of a, so when we do algebra, we have to be consistent. If you label a bunch of things, then you try to group them together by the label. So I'm going to group a1 with u1, and I'm going to group a2 with u2. And maybe when I group them in this way, the first factor is x minus 1, and the second factor is x plus 1. This is what I'm trying to do because this is what the example told me that I should do. That example was obtained in this way. So maybe if I want to obtain other examples, then this is what I should do. So I take a1 u1, and I write it as x minus 1, and a2 u2, I write it as x plus 1. I don't know who x is, but I have two linear equations, and x is is the common unknowns. What do you do when you have two linear equations that have x in them? You subtract them, you eliminate x. Why should you carry him around? Eliminate x, and you just get one equation. The equation is u2a2 minus u1a1 equal to 2. And in practice, you know u1 and u2 because they are somehow two cofactors, two factors that you got from 10 to the m plus 1. So if somebody gives you two numbers, let's say, let me give you two random numbers, 5 and 11, and asks you to find integers such that 5a1 minus 11a2 equal to 1 or equal to 2. Do you guys know how to do that? That can be done using the Euclidean algorithm. It's an algorithm that's more than 2,000 years old. So what you do, you basically take, let me work out that example. So I start with the piece 7 and the piece 143, which were 7 times 143 was 1,001. What I'm going to do, I'm going to do long division. I'm going to divide the bigger number by the smaller number. I divide 143 into 7, and I get a quotient of 20 and a remainder of 3. Now I take 7 and 3, and I divide 7 into 3. I get 7 equals 3 times 2 plus 1. So then what can I do? I can single out this 1, and I can put 3 times 2 in the other side. Then I can use that 7, that 3, sorry, and I can write that 3 is 143 minus 7 times 20. And look what I got there. I get 7 times 41 minus 143 times 2. But this is only for the number 1. So I can multiply it by 2, and I already got a solution. 2 is equals 7 times some number minus 143 times some other number. And now I know what the numbers are. The numbers are 82 and 4. Yes, and 82 and 4 work. So if I multiply 82 plus 4, I get 328. And sure enough, 328, if I join 329, I get the square of 573. But every time I have one with plus, I have one with minus. Basically, I can change the signs, or I can perform some little operations in there, and I can also write it as 143 times 3 minus 7 times 61. So if you look at the third row of my calculations, who are the numbers 3 and 61? Are exactly the a1 and a2, the ones that I got by starting with 183. So I didn't now start with 183. I started with 7 and 143. So I got 3 times 61, which was 183, but I additionally got 328. So guess what? So this one, I solved these two equations. There's a typo there, that 78 should be 7. I started with the pair 7 and 143. 7 times 143 is 1001. And I solved those two equations in A1 and A2, which are both linear. And I can solve them using the Euclidean algorithm of finding the greatest common divisor of two numbers by successively dividing the larger number by the smaller number, getting some remainder. Then I divide the smaller number by the remainder, I get another one, and so on. And I got two solutions, 61.3 and 82.4. So guess what? Now you can ask me some questions. Are all the answers obtained in this way, not only for the case 3, but whenever I find some example that works with some digits? Is it always the case that this is how I'm going to find it? I'm going to take 10 to the n plus 1. I'm going to write it as a product of two u's. And then a's I'm going to write as a product of two a's. I'm going to group them, subtract them, that equal to 2, and then apply the Euclidean algorithm. And the answer is yes. All of the solutions are obtained in this way. Question, is it always the case that the solution that I get has exactly m digits? So all these questions were addressed in my paper. For example, there I showed that any solution to this problem indeed is obtainable in this way. That number can be written as u1 times u2 with co-prime u1 and u2 bigger than 1. They have to be bigger than 1, otherwise your answer is going to have more than m digits. This is true if and only if 10 to the n plus 1 is not prime. That's why it didn't work for 11 and 101. But every time 10 to the n plus 1 is not a prime, it's going to work. Also, prime powers cannot be written in that way. And at the workshop, I did something similar towards the end by showing that 10 to the n plus 1 is never a prime power of exponents strictly bigger than 1. It could be prime. There was a problem open for some time. It was called Catalan's conjecture. It was less famous as Fermat's last theorem. Who knows Fermat's last theorem? Do you guys know Fermat's last theorem? What does it say? It says that you can never find two nth powers with n at least 3, which sum up to another nth power. You can't find two cubes summing up to a cube. You can't find two fourth powers summing up to a power. It's called Fermat's last theorem, but Fermat never gave a proof of it. He was reading Gauss's Disquisitiones Arithmetica book, and he wrote some text on the margin saying that he knows how to do it, but the margin is too narrow to contain his proof. And people have been looking for his proof since then. All right, so Catalan's conjecture is the statement that 8 and 9 are the only consecutive powers of exponent bigger than 1. And that one has been proved just a few years ago by Preda Mihailescu. So for example, the answer whether the number that you get in that way always has m digits, the answer is no. For example, if you start with 11 and 91 and you play the same game, you get A1, A2 is 25.3, which gives you the answer 75, but A should have 3 digits. If we lie and pretend that it has 3 digits, so we write it as 075, then it works. You get 075, 076 is 274 squared. However, you can always take the other one. If one of them is short, the other one is big. So the other one in this case is going to give you 66.8. So the one obtained changing the sign. 66.8, you multiply them, it's 528. It has 3 digits, and it gives you a solution to the problem. Now the interesting thing about it, how long do I still have? 5 minutes? All right. So as I was doing this, I said, well, let me write some computer program, because it's not so hard to write a computer program which will take some m up to 10 and will factor 10 to the n plus 1. It's not such a big number. It will find it. And it will look at all the decompositions, u1 times u2, where u1 and u2 are co-prime, and will find all those solutions just to see what kind of numbers I get. And as I was looking down the line, I saw 666 times 8. Then for m equals 6, I saw 6666 times 68. Then for m equals 9, I saw 666666 times 668. And I said, no way, this can't be incidental. And indeed it wasn't. Because I did that computation, I could prove the following theorem. Suppose that you have a number m, you take the number of 3m digits, which is a string of 2m6s, multiplied by a number which has m digits, so that the first m minus 1 are 6 and the last one is an 8. Then that one works. Of course, I wouldn't have noticed that it worked unless I would have done the computations for m equals 3, 6. You can prove very easily that a is at least 3 times 10 to the 3m minus 1, and it's at most 5 times 10 to the 3m minus 1. So it certainly has m digits. It has 3m digits, sorry. And then you just write down what it means. A is 6 over 9 times 10 to the 2m minus 1. A plus 1, then the other factor is 6 over 9, 10 to the m minus 1 times 10 plus 8. And then you get some expression. That expression, you have to multiply it with 10 to the 3m and add a plus 1, and that's where the algebra becomes useful. You get that complicated thing. You say, let's make x equal 10 to the m. So I get an expression that looks like 4 9ths x squared minus 1, x plus 2, x cubed plus 1 plus 1. It's a polynomial of degree 6 with leading coefficient 4 9ths. Well, guess what? I fed it into some computer because I'm too lazy to factor polynomials by hand. You see, I'm a research professor. I can't really solve a quadratic equation by myself. I need a computer program. So I put it in there, and sure enough, I get that it's a square of a polynomial of degree 3. So this is why it always worked. And I found an interesting example. All right, so maybe just the last minute or so. I gave m various values. For example, look, here's a number that you can impress people with. You take m equal to 4, you get that 12-digit number, 4445333288888. And if you take that number and you stick in the next number, then you get a perfect square. And you can keep on going in this way. You know, you're going to get a very big number. And as I was preparing this talk, I was in Bonn, and my colleague Igor Sparlinski from Australia, who has even more papers than I do, he said, what about concatenating a with a minus 1 to get a square? Because he thought that would be difficult, because if you play the same game, then instead of having x squared minus 1 on the right, which you know how to factor, because it's x minus 1 times x plus 1, you have x squared plus 1, which you can't factor. But still, just because I can't factor, you see, I am a very persistent guy. That didn't stop me. So I know a little lemma that says that if a number is the sum of 2 squares, if I take a product of 2 numbers which are both sums of 2 squares and I multiply them, then I get a number with the sum of 2 squares. That you can do it with, you can just check it. The formula itself comes from complex numbers. So I can do it in that way, and I can create examples. For example, here's, I'm just going to flash some things at you. Here's one example that I created in that way. For example, I take A242, and I put A241 to it, and I get the square of 9,079. I also get short examples. I get the example 85, for example, which is too short. I have to put 2 more zeros in it. So the question there becomes, similarly, if m is an even number such that 10 to the m plus 1 is not a prime, then you can do it. I have an algorithm that does it by using the fact that 10 to the m plus 1, if m is even and not a prime, it admits a representation as a sum of 2 squares, which is not the trivial representation, 10 to the m over 2, everything squared plus the square of 1. And I can use that and multiply, except that my answer now, it's not going to be a product of 2 numbers, it's going to be a sum of 2 squares of other numbers. So you see, sometimes in order to conquer equations, you just don't have to look at them as a linear thing. Sometimes you have the answers come as a product of 2 things or as a sum of squares. All right, so let me say some conclusion here. So the article explores the topic of creating perfect squares which have interesting digit patterns. We started in some easy way concerning the fact that every square, either the last or the one before the last digit, is even. And if you're in a more advanced world, you can link this with congruences, modulo powers of 10 that pick up last digits. Then you moved on to adjoining 2 equal blocks of digits and getting a square. And once you moved on into concatenating a and a plus 1 to get a square, you get to things where you have to use the Euclidean algorithm for finding the greatest common divisor of 2 numbers, representing it as a linear combination of the 2 numbers involved. When I concatenate them in the other way, I even get problems related to representations as a sum of 2 squares. Here there's a big theory in there of Gaussian integers, which is like the integers, except that it's the integers at which you adjoin the square root of -1. and they have nice arithmetic. So everything I did, I could have done it in that language. I did not want to do it in that language because I was afraid that you will all run away and I'll speak to an empty room. I just wanted to show, look, if you have a sum of two squares and you multiply two numbers of that kind, you also get a number of that kind by some easy identity. And there you can go further and explore other concepts like quadratic reciprocity. So this is just the tip of the iceberg. You can go further than that. And the only interesting thing is that I showed you some examples which you start with some equation and you find solutions, which I think is great, because if you wouldn't, then you would have felt like it's cheated, you do all this work and you get nothing. And I'm going to stop here. Thank you. Should I ask for questions, or do you ask for questions?
Colleagues, it's time for questions. We're only working with squares and digits. We start from foundation phase onwards and move on. He was just playing with some digits. In his own way, of course. Any questions, please? Any questions? While, yes, okay.
Good morning, ladies and gentlemen. This is not a question, but a comment. Just 2 words, thank you.
Okay, if there's no question, no further question, just to my colleagues who are involved in teacher education, can you see how you can deal with numbers and squares from an advanced perspective, which is relevant to what we really need to know about? So here's opportunities of recalculating teacher education from an advanced perspective. And I want to say, on behalf of AMESA, thank you for sharing to us the aspects, which I watch very carefully, is how you make your conjectures and how you go about proving them. I think the process that Luca showed us is what is important, and how you generalize, and how you justify, and how you prove them. I think that's what we need to be engaged in, the processes, if you got lost to the mathematics. Okay. And on behalf of AMESA,
All right.
Rajan, yes.
Oh, there's one question.
Just had this thing pop up in my mind. Base 10 is not a prime base, so do you get any advantage if you work on such problems with prime base, prime number base?
Thank you for the question. Certainly it's very interesting. I didn't think about it. I think this has more to do with the factorizations of the prime base plus 1 rather than, so I never used 2s and 5s in some sense. I used 11, 101, and so on. So it's rather what's happening after you raise your base to some power and you add 1 to it, and that's number you have to break it and so on.
Thanks. Just a comment. When we were discussing this paper, I told Florian just to keep it to the level, because we have a diverse group of people. But I think what's fascinating about this, he did so. I mean, I use this a lot when I'm training Olympic learners, grade 8 to 12. So it's important to know the background of numbers. Okay, not the proofs as such, but just the rules for divisibility, 11, 9, and all of that. And you look at some fascinating problems and how you can reduce it, bring it down to an easier level if one can engage with our level. So thank you very much from my side.
Thank you. Thank you.
Round of applause.
On behalf of AMESA,
All right.
we're going to say thank you for your
Thank you.
presentation and your time and informing us of some new theories and discoveries that you've made. And we're really proud to be associated with a person who published 500 papers.
Thank you. Thank you.
Thank you.
Thank you.
Okay. I just want to make an announcement. Ravi, Florian, Busi, and Stay. Around past 11, meet me at the door.
Can I get my stick?
9:75.
Did I get my stick from
11:10. Your transport will leave you the airport. And the National Council at 12:40, you meet me at the Pumi, right? National Council at 12:40. Okay, thank you very much. We now hand over to the President.
Thank
We
you.
have a closing ceremony shortly. We're just waiting for the LOC. In the meantime,
Thank you.
Yesterday, you had your discussions in your face committees.
Thank you.
And you also gave out evaluation forms.
Oh, thank you.
I invested.
Now, the appeal to the face committee conveners.
That's what they pay me for, yeah.
At the reception from you, get that and heard it. Also, the other thing, one of the questions was the new, the proposed passing or removal of mathematics as a passing in grades
Yes?
1 to 9.
Oh, yeah.
You have to start in your face and that because I've been approached by newspapers about that, and I gave my personal review. I said, these are local Herald, and today's Soviet. Okay, I give my personal view, but we will give a AMESA view once I collected the information from the face committee about the proposed dropping of mathematics as a compulsory passing in grades 1 through to 9. And that will only be done once we collect all the information. So just a reminder, the evaluation forms for face conveners to leave it outside at reception there. And the other important information is that face committee chairs must inform me what the decision was regarding grade 1 to 9 removal of mathematics as a compulsory part. So thank you. We'll just wait for the LOC, for Dr. Murad and company to come through, and we'll start our closing ceremony shortly. So thank you very much. I will address you during the closing ceremony.
Can I have 5 minutes? Can I please tell me something from
This mic up, are you closing? Okay.
I know when I do that at the airport, they brush me like that, they go between my legs and everything else. What's up? Yeah, come on to the program director. Okay, beyond. If I can do that inside, I need 2 bags inside. My phone I don't need. Hi, Nico.
Can you see? Okay, good. That's fine.
Without going to anything, is it fine?
And then
Sponsors Award. Who does that?
Yeah, there's
Who does that?
Sharp.
Sharp?
Sharp and Casio.
Okay. Cashier's here and Sharp is here.
Casio, yeah.
Who does the Sponsors Award?
They will come. You just call them and then they will announce.
They will come.
Yeah,
Sharp and Cashier.
Yeah.
Testing 1, 2, testing 1, 2. Good morning, ladies and gentlemen. Good morning. How are you today? You are fine. You are fine. AMESA rocks. AMESA rocks. AMESA rocks. AMESA is on fire. AMESA is on fire. After 1 week, you are on fire. Are you on fire? Excellent, excellent. We are coming to the end of our week-long AMESA 2017 Congress here in Port Elizabeth. Here in Port Elizabeth, we've had a good week together. The weather, who said the weather must be good? Someone made a phone call to someone, I don't know who. And they said the AMESA delegates are coming from everywhere to Port Elizabeth. Keep the rain away. Keep the wind away. And we saw we've had beautiful weather over here for this whole week. Okay. My closing remarks are very simple. I think I want to say we had a wonderful week together. Things worked very well for me and my LOC, who I will thank a little later. You have been brilliant. You were great. You stuck to your times. The success of a Congress is based on the delegates and their participation. The report I got and the feedback I got from the presentations, they were all excellent. So everything has worked out very well. We had very few incidences. I feel very sorry for the gentleman whose car was broken into. I'm so sorry. If you don't know, there was a car parked out here, just out here, and then the security people came to me and said, there's a car that has been broken into and had a GP registration. I am so sorry for that loss. I'm not too sure what has been happening. The other incident, of course, that we had was the person who accidentally took away the cell phone. And I'm not too sure if that cell phone has been returned. But other than that, I think we've had a wonderful conference. It was great having you all together to be here in Port Elizabeth. I hope you enjoyed yourself in PE. Did you enjoy yourself in PE? Yes. Excellent. I heard last night when I was home by about 10:30, quarter to 11, but I heard the dancing went on to 12 o'clock. But the winners were Eastern Cape, eh? They know how to rock and roll. All right. Right now then, I want to keep this program very short, simply because I know many of you have to travel long distances. I see the bus to Limpopo is waiting. I see the transport is ready to take you people back home. Some of you have to go as far as Mpumalanga and Northwest. There were lots of Northwest people yesterday. Yeah, there were lots of Northwest. And they can dance too, I can see, eh? Yeah. So there was lots of Northwest people over here. I think this week has been not only exciting for you, but I must tell you something. It has been exciting for me as well. I thoroughly enjoyed it. The complaints that you had very few people came to me and said, like they normally do, sir, I have a problem. But very few. I think no one came to me to say, sir, I have a problem. But thank you so much for that. Right now then, we have some sponsors award, and I want to call upon the sponsors. Casio, will you come up first? And there are some awards from Casio. So let's give Casio a big round of applause. And I want to tell you people something, that Casio has been a firm sponsor of AMESA. They believe very strongly in AMESA. So let's give Casio another round of applause. And here comes Astrid. When I saw Astrid on Monday morning, when she came from her hometown to PE, she was saying, I'm feeling very fluish. But after a week in PE, she's looking like 100%. Over to you, Astrid.
I might look 100%, but I've got no.
Oh, okay.
I'm going to hand over to Mac. We're going to do our draw for our competition that we did running for 4 days. Okay, the prizes are label printers. You all filled in the competition and we marked them, and the ones who got full marks, we're now going to do a lucky draw for 8 label printers.
Good show.
Are you going to draw for?
I'll draw for you.
Okay, first one.
First one. I don't know who I'm picking over here. Alright, must I pick you? Yes. Let's see who this person is. The person is age 22. Children 10. I can't be right. Lesejo Makete. Let's give a round of applause to Makete Lesejo. So careful. She is 22. I was right. Congratulations, ma'am. Well done. Beautiful prize from Casio. Excellent. Let's take a picture. I'll do that. Thank you.
There was only one right here.
And the next one, the next prize goes to, wow, a person who is round, looks like a hexagon, and the person is Audrey Gilfin? Andrew Gilfin. Is Andrew Gilfin here? Andrew Gilfin is not here. Are we? You're going to post it to him. Okay, he's not here. I think next time when we do this, we must say, you must be here. I think, but this time we'll post it. But next time we do this, we'll say, you must be here. Otherwise, one of you could get this prize. I must remember that for next time. All right. Are you lucky today? Are you feeling lucky? Let's see who's feeling lucky. Who's the lucky one? The lucky one is, oh, LCM. He is from the school Xingguedi. Xingguedi. It's Nobela Dan. Is Nobela Dan here? Is Nobela Dan here? Dan Nobela. Is Nobela Dan here? No. Then can we post this one as well? We have to post this one as well. How many more? How many more prizes?
This is number 4. We're halfway. So there's
Right. Now, lucky winner number 4. Let me take this one from the bottom and shake this box well. There we go. I am just taking the one that's just in my hand now. Let's see. And the winner is from Molwatsi Secondary, Martha Mashau. Right in front over here. Let's give her a round of applause. Well done, Martha. Well done, Martha. Is she from Limpopo? Well done, Limpopo. Okay, right, here we go. Next prize. We've done 1, 2, 3, 4 so far. We're halfway through. 4 more prizes. And the prize goes to, from Limpopo again. It's Limpopo's day today. And it is Langa Pretty Nakele. Well done, Limpopo. Here comes the prize. Yes. Well done, Pretty.
choice of 2.
Okay. This one goes to, the school's name is Zola. Who's from Zola School here? Let's see. Zola, Z-O-L-A. I don't know where Zola School is. But the winner is Ludwig Bauer. Ludwig, is that you? Hey, let's see him coming down. Well done, well done. Yes, it is him. It is Ludwig. Well done, Ludwig. Thank you. Well done, Ludwig. 2 more prizes to go. 2 more prizes to go. And this one here, this prize goes to Komotso Mumtitlani. Komotso Mutlane. It is from Tumagole School. Tumagole School. Where is that school? Is that her? Let's give her a round of applause. Is that?
She's already gone because of the flight. Can I take it for her?
She's already gone from the flight? Are you from the same school?
Yeah, from the same region.
Same region. Are you happy to give it to her? No.
Okay, you
No, they'll post it to her. Sorry, ma'am, but thank you for coming down.
There's one.
Okay, last prize. Last prize. I must tell Casio next time to bring 900 prizes, so we all can get a prize. Cassio, take note. Okay, this one is Ort SA, and it is Julius. No. Not Julius Malema. It is Julius Podun. Well done, Julius. Julius, please teach all our Julius brothers how to do maths. That goes there. Do you want to say a few words?
Okay. No, I
You can't.
can't.
All right. Astrid is saying she cannot say a few words because of her voice. She's not fully recovered yet. But I think we are very grateful to Cassio for sponsoring these prizes. Let's give Cassio a big round of applause. Thank you. Right, and now we call upon Sharp. Let's see how Sharp is. All right, over to you, ma'am. How many
Hello,
points?
everybody. Have you had a good week? Yes. Did you party hard? Yes. Are your heads sore this morning? No, okay. So this year we did the same as we always did with drill mode. And because we always have the same first place winner, we've decided to give second place the same prize as well. Okay. So, in fifth place, tied at 59 seconds, is Mankati, Ma'am Mankati, and Miriam Kanyano. Are you guys here? No. Oh. Can I say it again? Miriam Kanyano. Did I say it bad? And Mankati Ma'am Mankati. Yay!
Kareem.
Is Tema Algorithm from St. Paul's Primary School in Free State. Okay, in second place, winning a prize. She's at a secondary school, so we're going to send her the new senior quiz calculators. 40 goes to Marsha.
dance movements over there? Some quick dance movements? Some quick dance movements, Tabo?
Ladies and gents, before I leave, I want to say thank you again for an awesome conference. We've really enjoyed spending time with you and working with you guys. And as part of CERTEC, who distribute sharp calculators in South Africa, we want to work with you. Okay, so if you would like to order calculators directly from us, we will give you dealer discount pricing. In other words, you will get the calculators for a heck of a lot cheaper than you will at school. We also do photocopiers, interactive boards, TV screens, microwaves. So whatever you need for your school, please do contact us. We'd love to help you with outfitting you with the best possible solution for your students. Okay, thanks guys. Safe travels.
Thank you. Let's give a round of applause for Sharp and thank you for this conference. All right, as we move on with the program now, we are going on to a few people that I need to thank who assisted in making this conference such a huge success. All right? And firstly, I want to thank all the plenary speakers. I see Ravi's just walked out over there now, but all the plenary speakers and all other presenters who sent in their abstracts in, sent in their papers in. Thank you so much. Without those papers, we would not have a conference. To all the others who did not present, please think of some ideas next time as well. And we want to see you also presenting. No matter what it is, you can call it how I teach something, how I teach fractions, how I use resources, whatever you want to do. Please, each and everyone can present. Like you present your lesson in class. Let's run a workshop over here. You can do it. So presenters, thank you so much, and all the plenary speakers. Then I want to thank the catering department, the catering section, Faith and Rory, and all the people that helped for making all the lovely dishes for us. It was just wonderful for the week. Thank you so much. There was also a number of people in the background, the cleaning staff, cleaning up every time, making sure the toilets were clean, the place was clean. Thank you to them. The security, we saw them all the time over here, also trying to make sure that you are safe at all the times and be visible. The people that put up the tent, I think the tent was a good idea, wasn't it? Right? We did everything in the tent, so that was great. For the cultural evening, those who presented, those who were there, thank you so much to all the dancers and the music guy. Faisal was awesome last night with his music, so thank you to the DJ. Then, we're coming now to the students, and you see them lined up over there. They all could stand. The students could stand. You'll see them all dressed in green today. Let's give them a round of applause. And I call upon the Congress Deputy Director to please come forward and hand each one of them a small token of appreciation. So, one by one, you can come up. It will take 20 seconds. If they come up at a second at a time. The first one is Zinzan. Come through, Zinzan. Thank you, Zinzan. Thank you to Aston. Thank you, Zinzan. Thank you, Aston. Thank you, Tawfiq. Thank you, Raven. Thank you, Mr. Jack, our security man. Thank you, Melissa, who was smiling at the help desk all the time. Thank you to Roxanne. Thank you to Ashika, who assisted with the help desk as well and was there. Thank you to Adelaide. Adelaide, ladies and gentlemen, she is small, but she's so dynamite. And guess what? She is studying law. So wave to everyone, Adelaide. She's studying law. She's in what year of law? 4th year of law. So she's a future leader for next year. Thank you, Zuzifo. Kyle, where's Kyle? Is Kyle here? Oh, Kyle. Okay, thank you, Danielle, who was always smiling and ready to help everyone. Thank you. Thank you, Jeanette. Thank you to Hilburn. Not here. Thank you to Leandro, Joshua, our IT people in the rooms, Joshua. Thank you to Ryan. Ryan, who was here all the time assisting me over here. Thank you, Farik. There's Farik. Okay, thank you to Asira. Thank you to Azola. Thank you to Narissa. And Tanisha's not here, but thank you. Let's give them a round of applause for doing such a wonderful job. Thank you. They go back. And then, ladies and gentlemen, this whole conference would have not been a success if it wasn't without the help of our LOC. The LOC is a very, very dynamic LOC. And you'll see now in a couple of minutes how big they are. What a big group we were to make this conference a success. The first person I call upon is Sanette gone. Sanette Desel gone. She's not here. Karine, come forward, please. Let's give Karine a hand. She assisted on all the meals, assisted accommodation. She made sure you were in your spaces, in your beds, got your food, made sure the catering was done on time, checked on everything. Give Karine a hand, please. Thank you, ladies and gentlemen. Then we have Rochelle. Rochelle Stone's responsibility was registrations and everything else on that side. And although her portfolio was not in charge of the gala dinner and dancing, but last night she wanted to move. And that's Rochelle. Then we have Mendsidisi. Where is he? Big brother. Where is he coming? He was an all-round person and he managed the gala dinner program. Thank you so much and just being here. Then it is our Eastern Cape Congress Director or Chairperson. Where is small brother? That's big brother and that is small brother. Let's give him a hand. Every day he said he had to have a glass of whiskey in order to think about the Congress. But he did a wonderful job. Thank you so much for just being here. And then there is Herman Kemp, who was an all-rounder. Whenever I needed something done, I just used to say, Herman, come along, and she was there. Let's give her a round of applause as well. Not here today is Tom Pennington. He was our program. He did put the volume 1 and volume 2 together, got the papers together. And also our treasurer is Dudley Bester. He's gone to Bishop for a meeting. You know, the work must go on, so he's gone to Bishop for the meeting. And the other person is Sanette Desel, who's just our transport person and help with exhibitors and sponsors. And she's gone to the airport to take people back to the airport so they have to travel back. But this is our committee. This is our big committee that manages this whole conference. I think they need a round of applause. Thank you very much for that. Before they go, oh yeah, okay, we'll talk again. Thank you. Then, ladies and gentlemen, we can't forget the National Executive Council. Thank you to Dr. Gamanda and his team and all the councillors who are here from AMESA. Thank you so much for being here. Your presence over here made a big difference. It had such a calming effect on me because it just said, you guys are here, you take responsibility, and things just happen. Thank you to the treasurer. Where is Rajan Gamanda? Is he gone already? Oh, there's Rajan Gamanda. Thank you to him. Thank you to the president of AMESA. And then we mustn't forget one very important person. This conference would not have been possible if your registration and everything else was in place. And that person is Nombolelo. I think she deserves a round of applause, and it's so big that you can hear in Limpopo. Thank you, Nombolelo, for all your hard work. You put everything together. Working with 900 names is not easy. Nombolelo, stand, they want to see you. Please stand, they want to see you. Mandela did a stunning job. She did a wonderful, wonderful job. And she put everything together. Thank you so much, Mandela. Ladies and gentlemen, we can't forget there's two people I must still thank over here, and it's namely all our sponsors. I'll go back to the sponsors and exhibitors. The conference, this conference, I think the sponsors believe in AMESA. We heard this is the largest, almost one of the largest congresses in South Africa. We don't get 1,000 delegates very easy at a conference. We normally get 200, maybe 300. But 1,000 people that come to a congress is huge. And therefore, sponsors like Casio, Red Pencil, Sharp, and others, Xenex, they all believe. If you see your program, you'll find on the front page over there of the cover all our sponsors' names. Ladies and gentlemen, Sassoon Zalo. Last night we heard from Philip Ticomo. And now this is a challenge I will put out to you. Philip said yesterday, and this I will put a challenge to all Eastern Cape, all AMESA, what you call it, chapters? No, the districts. Regions. All regions. This is a challenge. Last night, I was listening to Philip Ticomo speak, and he's saying, if you want any development in teacher education, or anything that you want done to assist the teachers in your region, write to Philip and say, we need to do something to assist maths teachers. He said so last night. You don't just give. You have to ask, and then you're dead. I think it's very important that each region take note of that statement. Each region take note of that statement. You've got to work with national. Say, national, I want to ask for this program. I want to help teachers in this way. Put it out there, and let's see how Philip responds to that call. They may give you 50,000, they may give you 100,000. It will be something to assist teachers to develop so that the learning, teaching, and learning classes can be better. So regional chairpersons, where is baby brother as well? Please take note for the Eastern Cape, for the PE district, the region. We need to put out over there, write to Philip Ticomo, who is the Director of Math, Science and Technology at National, to say, here's a proposal. Can you assist us? Can we do something more? How can we make teaching and learning better? We saw from all the presentations, from Faiza's presentation, from other presentations, and they always refer to the TIMS, and they always refer to the ANAs, how poorly our children are doing. Under 50%. Why can't we do like the Japanese are doing, baby? Or what can we do what other people are doing to raise the standard? We need to do something. So let us take that as a challenge as we leave and think about that one. Then, we have to thank our lady who did the memorabilia. So Yuni, thank you for doing that. Thank you for helping us out over there and doing all of that. Let's give her a round of applause as well. I think all my thank yous are done. If I've forgotten someone, I apologize. But lastly, I can't forget you guys. I must say thank you to you. You guys were awesome, awesome, awesome. Give yourself a round of applause, please. All right. Just an announcement from Karine over here. Hostel door cards. Am I right, Karine? Hand in at security at hostel. All right, before you leave, please don't take the door cards with you. You have to return it to the security at the hostel. Then, I go on to the next item of the agenda, and that is launching AMESA 2018, and we're asking for Mona and Free State LOC. Who's presenting that one? Ah, there we go. A young man over here from the Free State. And he is Kosu Peko.
Let me take this platform to greet every one of you here, even the president of AMESA and the protocol of it. I'm not going to be for long. I just need to do something. We Free State people like peace, harmony, joy, friendship, you name them. Now, Mr. President, before I continue with the presentation here, I just like, because you are coming to us next year, just a welcoming song. Where is my choir? I need my choir here. What? Come over, please. And now, for the moment you all been waiting for. I said, we Free Staters like joyfulness too much. Now, coming to present, we just wish Ms. Melna, his mother is sick at the moment. We just wish her a speedy recovery, and may God be with her and bless her. Other than that, guys, let me just go on with my work. Coming to the Free State. Coming to the Free State, we are a place that is so beautiful, which is so adventurous. All the things in there, all the places, all the people are cantankerously loving me. Now guys, our place where we will be visiting is the place that is called none other than the city of roses. If you really need the roses, just come over to Bloom. I saw some of them that comes from Pretty Gardens. They planted them here. Those roses come from Bloemfontein. They come from Tuesday. I praise that Transvaal is there. Now, just coming to the theme of us. Our theme is just simple. Culture meets culture. I know there's going to be a question in most of your minds. What culture? We have the mathematical culture that we see is now drowning. We want it to meet with the higher level of mathematicians and maths as a whole. That's why we say culture means culture. Maths with us. And at the very same moment, I just want to thank all the maths people. You know, you can do all things, but if you don't have maths, it's like you are an empty shell. If you can't even count how many coins you have in your pocket, you are doomed. Now, there's a motto that I always use that says, you must aim at the sky and be on top of the mountain. Dr. Hilary Rue says in his words, I quote, you can't expect to survive on your name alone. Only your abilities will carry you through. Now, next people, le na le mosebetsi o mongata le tshwanetse o etse yet le ntse le etsa mosebetsi o motle bo nka le lakaletsang ngwana gore le tshware ka thata le hodise tšhaba sena sa rantsho rona mo re tswang teng ke tla ke ipoka dipedi math is in us, around us, and with us, because everywhere we go is math. Just the steps that you take while walking is math. You can measure the steps, you can count how many steps you walk, that's math. Just going around the circle, it's how many degrees, sir? Sir? How many degrees? All right. You can see now. The only thing that made Eastern Cape to beat us in dancing is because the only thing that they can do, and they don't do it in a correct manner, is done in this way. Not. All right. I'm just making a joke there. And then, here's the thing. It says the conductor of an orchestra doesn't make a sound. He depends for his power on his ability to make other people powerful. That's what you must do. You as a teacher, you are like a conductor. And you depend on one another and on the kids to make mathematics a success in this country. I'm sure by 2018, even, let me say 2017, we are only having 100% here. If your kid doesn't get 100% pass, please make sure you are on the first flight or bus or taxi or cab to Free State. And now, the place where the AMESA will be held the University of the Free State. It's one of the biggest universities. Let me show you one thing. Free State is a bigger place that has one of the townships that rates more like Pretoria. Do you know a place called Botshabelo? That's the second largest township in South Africa. Believe it or not. Now, yours is going to be the place that you are going to be attending to. And I know a lot of you says, the Free State is so cold. These are some places that you are going to attend to. You can just check, everywhere it's roses. Now, the date, 25 to 29 June next year. Okay. Chair, I think I'm going to need your protection here. We know that it's winter and it will be cold, but don't worry. The hostels has got what? A central heating. Because we know most of the people, so don't worry, just come, you'll get warm all the time. Now, this is our core LOC. This is our core LOC. The Congress Director, which is Anari Milne in her absentia. The Deputy Congress Director, Sillo Mutswani. And the Academic Coordinator, which is Prof. Karen Champura. I think you'll see others when we arrive in Bloemfontein. If I can tell you all of them, some of you might say, those are just high experienced people, so we don't need to go there. Now, the Free State is welcoming you, and we are looking forward to see you in 2018. Now, before we close, there's just a clip I want to play to show you the place, the entire Free State. I don't think I'm not going to have a sound here. All right, but you can see that's the beauty of the Free State. My time is up. That's just it. And when I go down, will you Free State people please just take me down with a nice song? We are near a PSL team that has most fans, the Siwelele one. If you can just hit us and then I go also. Thank you to the president here and all the sponsors. I didn't got a chance to thank the sponsors. But most of us depend on the presentations and things that are done here so that we can make better of our children.
Thank you.
All right, good people. You must not leave the chamber. The president has to speak. All right. Thank you to all of you.
Thank you, Free State. Yes, we are going to be Free State. Give the Free State a hand. Thank you. But before we hand over to the first invite Philo, Seno, what's your Deputy Congress Director, sir? Good. Okay, let me hand over the baton to Free State. What Free State needs is inside this bag. You know what they need? They need lots of wine to take them through to Congress 18, to planning Congress 2018. So all the best to you, sir. And inside here is a few ideas of how to manage a Congress. I put it inside here to say, please think about these things so that we can have a smooth Congress for 2018. Over to you, sir. There's also a name tag over there for the memorabilia lady, if you want to use her. All right, thank you very much. I now hand over.
All right, I thank you again to the Limpopo, to Eastern Cape. All right. Just to save time, we'd like to thank you, and we'll use each and everything that you gave us, the ideas that you gave us, just to go further. And as you can see, it's green. Siwele.
Thank you so much.
Thank you, Free State. Thank you. Before we end, I just want to, on behalf of the LOC, to hand over special token of appreciation of the LOC, in fact, of all of us present here at Congress 2017, to the Honorable Dr. Tulsi Moral. Give him a round of applause. Right, just a quick, all the thank yous have been done, but I'll be feeling my duty if I, on behalf of AMESA and the National Council, to express thanks to the following persons. Our guest speakers and panel discussion members, our presenters of papers, workshops, our teach sessions, posters, and math markers. That's what makes the Congress. Our sponsors, and we have two wonderful sponsors, Casio and Sharp present with us, not forgetting Zenex and all the other sponsors. Without the sponsors' contribution, you'll pay a lot more to attend the Congress. So give them a round of applause. The Nelson Mandela University, well, it's still Metropolitan University, but on my birthday, which is the 20th of July, right? This is a very significant day. It becomes Nelson Mandela University. The LOC members, as we mentioned, led by Congress Director Dr. Tulsi Moran and all his helpers for their very, very hard work. If you only knew what went behind the scenes, you will be amazed. Thank you very much. A round of applause to them as well. To our LOC members, it's the National Organizing Committee. Some of them are not here. They've taken people, they've gone already. They work very closely with the LOC. But by and large, the work was done by the LOC, and we helped where possible. And lastly, to all participants in the 2017 AMESA National Congress, we thank you for your patience, especially on Monday, for your kindness and constructive engagement with both our academic and social program. Just one last thing, just to remind you about the evaluation forms to leave with reception before you leave. The FACE committee convenes to send their reports ASAP, and the regional committee chairs to also send those reports, because it's on those reports, which represents our members' feelings, that we engage with the Department of Basic Education. I trust when you leave today, Friday the 7th of July, it will be with fond memories of our 23rd Annual Congress, held in what I would say the friendly province of the Eastern Cape. As Free State have indicated, they have promised us a wonderful, exciting Congress for 2018, and we look forward to that. From my side, thank you very much. We'll now close. In fact, I now declare the 23rd Congress of AMESA 2017 closed, but as to observe the protocols, let's finish off with our national anthem.
Thank you very much. Can you all please stand and rise while I call upon Delaware to lead us with the national anthem. Come forward, Delaware. Here we go. Keep it close, eh?
Thank you, sir. Let's all sing the national anthem. Kosi sikeleli Afrika, malubakanisu kolonayo, izaleni tandazo yetu, kosi sikelela tina lusapolayo, morena buluka sichabasa Yesu, ufedise vitali matele, usibuluke, usibuluke, sichabasa Yesu, sichabasa South Africa, South Africa, et glow van onze Heere, en die diepte van ons Heer. Ons Heer weggegeven, wat die kranse antwoord geeft. South Dakota to come together, and united we shall stand. Let us live and strive for freedom in South Africa.
Ladies and gentlemen, the conference is now closed. Please travel safely home, and God bless. Thank you.